There's a lot of information in this problem, so let's cut to the chase, and then maybe that can help us sort through the information. What is that maximum profit from manufacturing both phones? So it looks like there's two phones, a basic model which I'll call X and the Pro model I'll call Y. So X will be the number of basic phone models we create, and Y the number of Pro models. Basic model generates a profit of $100 per phone. Here, basic, let's do 100x for our first equation. And the Pro gets 150 per phone. It's not an equation, that'll be an expression. This is profit. I'll just write equals profit. That's probably what we're going to have to maximize here. On the assembly line, the basic phone requires 7 hours. So 7 times every number of phone for basic that's made, 7x plus 11y. This is assembly time. And the basic requires 1 hour, and the Pro phone needs 3 hours for finishing. Which includes loading software. Okay, we don't care about that. Both phones require 1 hour for testing, so x plus y is testing. On a particular production run, the company has available 1,540 work hours on the assembly line. Okay, so they're telling us what this equals. So the total amount of hours we can do for assembling is 1,540. Total for finishing is 360, and total for work hours, which is 200. So we want to maximize this function. What we need to do is we got to graph all three of these constraints, and then we'll find the maximum value by considering the extreme values on those constraints. So you'll see what I mean in just a second. So we got to graph all three of these equations. Quickest way would be to consider just positive x and y, because we don't care about negative number of phones produced. And then define the intercepts. So if I plug in 0 in for x in this top equation, then we're going to have 11y equals 1,540. So that gives us, oops. Oh, I typed it in wrong again. It was 1,540 divided by 11. So that's 140 for the y-intercept. Plug in 0 in for y and solve for x to find the x-intercept. So I got 220. Those are going to be no, we're going to have 360 down here for an x-intercept. If you plug in 0 in for y, you get 360. Plug in 0 in for x, you get 120. And then here you're going to have 200 for the y. Try to keep it consistent. And then for the x-intercept, you have 200. Just plug in 0 in for y, solve for x. That way we can quickly graph these. So it looks like 360 is my biggest in the x-axis, so let's go by hundreds. 200, 300, 400, so this will be 400. And then for y values, the biggest we have is 200, so let's go by 50s. 50, 100, 150, 200. And we'll graph each of these lines. I'll use a different color. Oh, this will be red. So 220 on the x, right around here, 0 for y. 140 on the x, 0 for x. 140 on the y, 0 for x. There's our first constraint. It's got to be something less than this. It's got to be going in this direction, because you can't have more than 1,540 assembly hours. And we'll do the same with this one. We'll graph using the intercept. So 360 on the y. So if that's 300, then this is about 360. 120 on the, that's 360 on the x. 120 on the y is right here. That's a terrible line. Got to get it somewhat close. And then last one we'll do a lovely green. So 200 on the x, 200 on the y. Oh, so because I'm just sketching a graph, it's actually hard to tell. It might be better to use some graphing software. Look, because you can't tell if green or red actually. So if it's a test, and if you don't have access to graphing software, you just got to sketch those lines again. Just be really careful. I did it kind of quick because I'm making a video. So there's one equation. I'm in desmos.com/calculator. Okay. So with all these, it has to be less than these lines because these are upper constraints. So it has to be below them. Except, wait, what was red? Assembly hours. Yeah, so I think we'd only want to consider this intersection and this intersection. The reason why it can't be this one is because 120 for x, 80 for y, that would be above this constraint. I put equals in here. It really should be less than or equal to, right? Because we can't go above these hours. So if you even consider this vertex, because what we do with these linear optimization problems is we look at where they cross. One of those has got to be the optimal solution, but I think we can even just exclude this one. If you plug in 120 in for x, got 840 hours for the basic phone, then 80 for y. That's above the availability for assembly hours. Yeah. So we can even just forget about this vertex. We want to consider this vertex or this vertex. Which one is going to maximize our profit? Once you've identified the vertices, then you go back to the expression you're trying to maximize. Plug them in and see which one makes the biggest value for profit. So 165 for x gives me 16,500 here for profit, and then 35 for y. 35 times 150 plus 16,500. So we got 21,750 for this vertex. Let me write that down somewhere. 21750. And then this vertex here, where they cross, 6698, so 66 times 100, 6,600. It's a little bit bigger down here, so it looks like the way to maximize your profit would be 165 basic phones and 35 premium phones. The way you do that, if you didn't have a graphing calculator available, is you have to plug. Once you fix your graph and you recognize that red crosses with blue right here, you'd want to solve this as a system of equations to find out where they cross, and then plug those numbers in here. Same thing down here. You'd solve these two as a system of equations to find out exactly where they cross, and if you do, you should get these two numbers. And then you plug them in for the profit to find out which one maximizes your profit. But when I plugged in both these points, I found out that this one down here was maximizing profit. The question says, what was the maximum profit? I think that's 21,750. I identified the vertex that gave us the maximum profit. I identified the number of phones, but specifically says what is the maximum profit. So if you plug in that vertex that we just identified, I think we got 21,750 in for profit. So that's the max profit.